notes?
No, I was going to start with that. Or we should do it
Like usually it's easier
to
to approach somebody directly because otherwise nobody will listen. You have to fill out the upper line.
I mean, you can describe as well, right?
Yes and no. So usually what I did, I also go in the Jabber myself and have a look at it because usually there's not too much going on, but maybe it's helpful to have one. What's the date?
Yeah, I don't have like.
So you have the slides on your
Yes.
computer, so I could actually go and I would.
Jabber.
Yeah, I would check Jabber anyway, but maybe it's helpful to have somebody set up.
But this will you will pass them now already. Do we have someone that Okay, so Brian is not here, so we'll give me the
he's usually our.
Yeah, you take the secretary.
Yeah, it's hard to see because you're very close to the scrap.
Okay.
And the Jabber strap maybe an easier job? It's going to be on Jabber?
Can you watch Jabber a little bit? I will also watch it. Yeah.
On off from this one. It's on. It's always on. Yeah. Oh, okay. You have to be careful.
Yes, yeah.
Exactly. Okay, when we are at 9 o'clock, so yeah. Okay. Welcome everyone to the Rmcat session. So my name is Anna Brunström. I'm one of the co-chairs for Rmcat. Martin Stimmerling is the other one. He cannot be here today, so he will join us on Jabber, I think. So Mirja Kulevin is no longer a Rmcat co-chair, but she's helping me out up here today since Martin could not be here. So thank you for that. And we got the note taker, so thank you, Alan, for taking notes. And Miriam Maroon will try and watch Jabber jointly. Okay, so let's see. This is the note well, and it applies, so please be aware. We have the remote participation, so if you and the meeting materials online. So all of you are, of course, here that I see. So you may not need it, but for the rest of you, we are having a number of working group documents, and we are actually going to cover all of them today in one way or the other. So for the working group documents where we do not have a longer presentation, we have asked for an update from the chairs, from the authors. So we will cover all of those to see what the status is and what the next steps are. So this is just to give you the overview and what documents were updated since the last meeting. So we still have the requirements document that is in the editor's queue, but all the other documents we will cover during the meeting and get back to the status for that. We also have 3 active individual drafts, and they will also be covered during the meeting. So 2 of them are new. We have the framework document that is now first version available, and we have a feedback message document coming out of the design team, and both of those will be covered in the meeting, as well as Varun giving a presentation on related to his draft on FEC and congestion control. We have a number of milestones that are past due, so we will revise them after the meeting and get back to you on that on the list with the new dates. So this is the agenda. It has been iterated on with some of you over email. So we will start with the overview of the documents that don't have longer presentations to see where we are. And then we have some presentations related to the feedback, to the framework document, and then related to the candidate algorithms, NADA and SCREAM, and some of the test cases that have been evaluated there, and then the FEC and congestion control. So unless there are any further comments on the agenda or bashing of that, we will continue. Okay, so then we move on to the overview of all the documents that don't have longer presentations. So we have gotten updates from the authors and combine them here. So for some of them, I will ask the authors to maybe come up and have some discussion because there are outstanding issues. And for the others, we will just go over the status and see that we are agreeing on where we are and what the next steps will be. So the first part is the app interaction, and from the history we have split that up into 3 different documents. So there's still the application interaction document is still missing. I think that the plan is that it should still come, right, at some point. Or you want to comment on that?
I think in
Name
Chen Varun Singh, I think we need to do it. I think the main reason we've been hesitating to get it out is, I guess, if there's enough energy if there's real need for it, apart from having actually the same taxonomy for everyone. Like if the application people will understand what the congestion control will do. So I think the main question we're asking, I guess both Stefan and I have been struggling to actually write this up, is if there's any interest, because the 5 people who use the documents probably understand the taxonomy. If there are other people in the room who would say like, yeah, I think this is very useful, I think would find more energy to do it.
But it could also be useful for other readers later, right?
That is why I said that we probably need to do it.
Yeah. Okay, anyone else want to have a comment on it? Otherwise, there will be a pending point that will...
Jahed, well, we're working on this framework document, and framework document says like there is some kind of interaction between the application and congestion control. And if we can cover that on framework document in a paragraph saying like this is what we have a mental model of it, but I think if there is any detail, more than that is required, is obviously the app interaction draft can cover. So I think there is a need that we still working on this app interaction draft and later on decide what to do with this.
Hi, Sergio Mena from Cisco. So at the moment, I will actually comment on it later. We are trying to maybe open source some setup where all the algorithms can actually be compared. And one of the things we are actually not sure what to do is actually that interaction. So, you know, guidelines in those drafts would definitely help. This like implementation that so everybody can agree on what we're doing there, and so the comparison is fair.
Okay, good. And the framework document we have now, so that we'll have a presentation on later on the new framework document. So this slide is really the update for the codec interaction. And the primary interface there is the allowed rate. This document has been waiting for the framework document. So I guess the next steps here will be to have a look at this document and see how it aligns with the framework document and if there are any modifications needed. So I see some of the authors nodding. So I think that the next step there will be that we will get some update to align it with the framework. Then we have the coupled congestion control. So this was updated before the IETF 95, and it now has coupling to both NADA and GCC. So this document is basically ready. So we have a dependence on the algorithms there. So this is what has held this document up a bit. So there's been a keep alive update. But what we will do is we will move this document to working group last call, but we will then hold it to see if there are any alignments that needs to be done with the algorithm before, pushing it in the final step. So the only thing that is needed there from the document perspective is something that applies for all the experimental draft, and that has been discussed between the chairs also in the TSV area, that we should have a section that identifies what is needed to take the drafts to the next step. And if we put that in before we put the drafts further, then we will smooth up the process, so it will go faster. And I did send a mail to Michael, but he did not read that, I guess.
Michael Wetzel, I'm asking here because it's maybe a good clarification for all of them. When you say next step, do you mean going from experimental to PS?
Yes. So to explain what you are expecting to gain from input from the experimental step, and maybe if there are some particular things that should be watched for in the experiments, or that we look for experience and feedback on.
Okay, thank you.
So this is something that we can also coordinate with the chairs, of course, when we need to add those sections in the documents, if you have further questions on what we are looking for and what should go there. Next is to share the bottleneck detection document. So this is also basically ready. So this was presented at the last IETF meeting, and there has been no updates on it since that. So it's the same thing there, that they will add a short section that applies to explains the step from the experimental, and then this document will also go to working group last call. Next is the eval criteria, and there I think there has been an update to the document that is not yet pushed, and that updates the jitter model primarily in the document. There are a few outstanding parts, and it's whether we need the loss model or the background UDP model, and Varun is coming up to introduce that a bit more.
Varun Singh again. So I think in Buenos Aires, we had some discussion about the background UDP. Kind of forget what the final outcome of that was. I think we landed on we need to write something up, and no, I think it already came up in the previous meeting before that, where someone said that they were experimenting with background UDP, and I thought it was a good idea to, if people were going to experiment with background UDP, that we have a section on it, or at least a short section, and in addition to that, we maybe define what background UDP means. The loss model, of course, we've used traces in the past. My main question there was, do we want to specify a model? Like there are already well-known models there, like Gilbert loss model, so we could just basically use one of those. And again, for those things, we would need parameters and values. And again, it comes down to experimental validation of the model. So I think if someone's actually used the model, then maybe we would probably just use that. And when people have experimental data to show that it works, then we can bake it in.
Sergio Mena. So a note on the background GDP. So yeah, we were experimenting with both the initial version of but that was not for the eval, it's for the test cases draft. So my suggestion is maybe that these drafts should somehow mention the fact that you can do actually we were using the background GDP in order to model the channel capacity, and actually the results we were getting, not surprisingly, are not exactly the same. So that was why it was interesting. So I would suggest that both drafts mention this in a coherent way.
Jahed, yes, I think that was the main reason this Varun brought up this up in the last IETF meetings. But when it comes to model, it needs to be defined in the eval criteria, and then basically from the test draft, we just say like you use this model. So yeah, so it's like really pointing to this model. Yeah.
Sorry. Just Varun Singh again. There is an editor's note in the draft. People who've implemented it can go and look at it. And there's very small guidance there to say how you'd create the background UDP. The feedback I'm looking for that is if that works or not, and if it's consistent with what you implemented. And if it is not, then send me a pointer and I'll fix it.
Stefan Holmer. I have one question about background UDP. Is that something that we are going to require, that all the test cases are run basically twice, once with varying capacity and once with varying amount of background UDP? And do we think that it provides enough value to basically duplicate all the test cases?
Sergio Mena, so this is in fact what we're doing at the moment. Whether there's enough value or not, we see some small differences in the behavior. Is that a justification for having them, duplicating basically the test cases? Well, I don't know, but I think it would be interesting to see how the algorithms behave in those conditions.
I mean, currently, Jahed, this eval test says like you should do it for both. But the reason was like, I think there was a discussion about it when Sergey brought it up, like they have seen some sort of different results. And I had the same question, but it seems like people are okay with adding it in eval test. So it was added. So basically, if we don't feel like there is no substantial change, we can say like this is optional or anything like that. But as long as nobody says like, well, we don't gain anything, I think it should be there because it actually shows some kind of different characteristics. So it might be good to have a look at it.
Stefan, yeah, I'm mostly wondering if this is going to show us something like, okay, this algorithm actually breaks under varying UDP, but not under varying capacity. Otherwise, I'm not sure it's worth basically doubling all the test cases. Maybe if we could cherry pick some of the test cases and say that, okay, for these few, it's worth doing, but it's not mandatory to do for all of them.
No, it's not mandatory for all of them. So there are two cases.
So Sergio Mena, so an extra thought on that. The fact that we're using UDP to model channel bandwidth, we're sort of killing two birds with one stone, in the sense that this is also modeling background traffic. I mean, these algorithms will deal most of the time with background traffic rather than with physical route changes or channel changes. So for me, like the background UDP is like a more frequent scenario where these algorithms are going to face in the wild.
Varun Singh. One of the reasons to actually do this would be to see the impact of the algorithm on the background traffic, as opposed to see what the if the congestion control breaks or not. So I think that's one reason why we would like to do it. One way forward is to actually bring out a new test case. We're not short on numbers, so 5.10 or 5.11, which says background UDP, and that's. Yeah, so instead of adding it to 5.1, for example, or 5.2 as an additional case, like an additional vector added as a different test case so that people just run it against that.
Yeah, Kulevin. So the difference is that if you have UDP background traffic, you can actually drop UDP packets. If you don't have UDP background traffic, you only will drop packets of your own flow. So that's the difference in behavior. And now it depends what the purpose of the test case is. If you only want to figure out how quickly your algorithm can adapt to these changing situations, it doesn't really matter. If you also want to evaluate the impact on the background traffic, then it does matter, of course. And by evaluating the impact on the background traffic means you need an additional metric measuring the loss on the background traffic. So that might actually be a different test case. So my recommendation would be use UDP background traffic. I would give the recommendation to use UDP background traffic, but wouldn't make it mandatory. Or just don't use UDP background traffic and have an additional test case to look at the loss rate because there you need it.
Okay, I think the eval test criteria now says like 5.1 you can run in two ways. One is this physical drop of bandwidth, and another is like the background traffic. And for background traffic, it should say like, okay, we are looking at the motivation here is like, what's the impact on the background traffic? So you actually look into the delay and loss on the background traffic. Yeah, that could be added. I don't feel like you need a new, because it's the same text, different test case. I don't need a new text case even if it is optional. I think now the text doesn't say like it's optional or anything, but it's more like a recommendation. You do that, and you also do that. You can also do in this way. So all you need to say like, okay, do both. And for when you're doing under the background traffic, look into the impact on the background traffic, not in plus the condition.
I feel what Sahid just said, maybe a good compromise, just doing both for 5.1 and the rest, just we pick one of two. This way we don't duplicate them.
Yeah, so I don't think you need to do both, because if you want to evaluate the background traffic, you have to have background traffic, and the only reason to not have real background traffic is because it's easier to implement. But it's a more realistic scenario. Usually you don't see big. Okay, you might see capacity changes because you have rerouting or whatever, but there's still usually some background traffic or whatever. So I think that's a more realistic scenario.
Jahed, I'm surprised that I'm saying that, but yeah, we actually down prioritize the wireless test case, where you actually change your bandwidth quite frequently, quite a lot. The jump we have in a physical is actually nothing compared to what we can get in real life. So basically, I don't see that anybody can escape the change. I see that's a must, and then background traffic, because what exactly the intention of having background traffic? As you say, it's impact on the background traffic, and what does it give it us? Analyzing impact on background traffic, what does it do? If background traffic is fixed rate, unadaptive traffic, and what do we learn from like looking at what it does to background traffic?
No, it's how you adapt if the background traffic changed, especially if you have non-adaptive background traffic where you suddenly have like a big flow starting, sending out all the packets. Then the question is, how much do you disturb this initial starting phase for the background traffic? Can you back off quickly, or does it take some time? In this changing situation, it might make a real big difference if you just change the capacity or if you start background traffic.
Then why do we look into the impact on background traffic?
Mike.
So I mean, I think the motivation here is like we would like to see the impact on background traffic, but now you were talking about how the adaptation actually behaves, and so
that's why you might just want to have two different test cases to separate those things out and not getting confused here.
Varun Singh. I think I'll endorse the second way. I think we need a different test case, because currently, as I read it, it's in 3 different cases, and actually trying to gauge what the impact of the background traffic in all these 3 cases would be quite difficult depending on each algorithm. So pick the first one and make a new test case where the background traffic increases and decreases. I think that's a different. I think we can take it offline and actually have a look at this. But I think the 5.1, modeling it around 5.1 makes sense.
Magnus Westland, Ericsson. I have an interesting experience from this week, and that's why I haven't sent anything to mailing list either. But it's ECN is clearly on the rise, and we have some things happening in. And I actually looked at there's no ECN doesn't seem to be spoken in the validation criteria at all. It's in the charter for being considered. So I do wonder about we actually need to introduce some ECN cases.
Varun Singh, did Magnus just volunteer to send us text?
I can take a look.
Thank you.
Okay, good. So it seems we need the background model, and we will have some updates also to align with the new test case and also getting the ECN in perhaps then. So the next one is the wireless test. So there has been no updates on that since the last time. So it's been some algorithms trying it out. So I think this one is ready for having a review, or you want to add something else about it?
Sorry, but I was just checking what Magnus says was, well, we have mentioned ECN. There is an potential test case section. There it says like you can run this thing with ECN enabled, same test cases. So that there is already an eval test. There is a ECN section. I mean, whether we would like to move it to the potential to the main use case section is up for discussion, but we have some. Eval test. No criteria. You should not look at the criteria. It's more messy.
So I think the tests are easy to just say turn on ECN, but I think the criteria requires some work in the sense that what do you want to like turn on, and what are you actually measuring, and what are you going to like compare things to. So I think that part requires a lot more thought.
Yes.
Hi, Colin Perkins. So, I mean, we've obviously had a lot of discussion of ECN around the circuit breakers. It's clear it's important, and it's clear this group needs to do something about it. It's also clear it's not as simple as just say turn on ECN. So I think we should be looking at that, but I would perhaps suggest the right thing to do is to make it a separate set of test cases. I forget what the drafts are called, evaluation criteria or whatever, and run it separately to the loss-based testing. I think it's a sufficiently big and difficult problem that we need to separate that out from the stuff we understand currently.
And Jahed, I think we discussed it, and the ECN and AQM, actually, we discussed it, like, what do you do? And the main thing was, like, how do you model the marking? And what is the interpretation of the ECN marking? I mean, what is the behavior you want? Because that's where, I mean, I have worked ECN-based condition control from very day one. I started to look into transport, and that was the main question, like, how do you transport this ECN marking to a rate? Or how do you really, for this case especially, how do you evaluate that is doing good or bad? I mean, I don't know. So going on the more details on how you run ECN test case is a bit up for discussion for now. But in the eval test criteria test, we just say like run this test case with ECN on. So you don't have a drop trail queue, you have some EQM marking ECN.
But to my understanding, all the candidates did not run any ECN-based tests, right? I'm not remembering to see any ECN test results. Mike, you need to go to the mic.
Does any algorithm run ECN-based ECN test case?
Yeah,
I think.
Hi, Michael Ramallah, Cisco Systems. Yeah, NADA has the ability to, based on what the marking means, adapt its parameters so that it could have a response to it. The real question has been heretofore, and we've interacted with the AQM group or whatnot, is what should we assume that the marking in fact means? And then once we know that, we can at least in NADA adapt to it. Now, I make mention of that because we're also developing a feedback for use here, generic feedback from Rmcat, and we plan on bringing back information on the ECN bit. So going forward, when we find out that those markings perhaps have different meanings going forward, or perhaps mark differently statistically over time, that at least NADA, and I presume the other algorithms, since they'll have similar forms of feedback, can adapt their behavior to what that is. So we're kind of future-proofing a little bit of the feedback so that we could, when we really understand what those markings mean in the day, and I fully agree with Colin's characterization of the ECN stuff in the circuit breakers group in TSV, we'll be able to do something with it. Right now, we're struck with, if we make a test case, we could react very well to what we've assumed in the test case. We have no idea whether or not that's a reasonable thing to do in the wild. So that's where we are. And if anybody else has any commentary on that, feel free. Thanks.
Ingemar. I believe for this classic ECN, as Bob Briscoe term to call it, and I believe it's reasonably clear how you should react to ECN markings. If you follow that RFC 13168, a sort of a regime. L4S is a sort of future headache, and there are some sort of indications where this is going as well. But
So
if you
sorry to interrupt you, for classic ECN, are you talking about using red as an AQM mechanism, or also like pi or CODL or whatever? Because
it's
quite different already.
Configure a delay threshold. And the trick is, of course, how to configure that threshold. Should it be 1 BDP or that sort of? You get into those discussions, and I don't know if this group has energy enough to spend a couple of additional iterations to formulate that. But through Ghost Scream, the C++ code doesn't have ECN support yet, but sort of the standalone code that we're running, it has sort of.
Did you also experiment with it? So did you run it with some, like which AQM did you use?
If you have a result with CodeL, and you can use that sort of as an indication how it runs. So that is all.
And this was with ECN, or?
It's not with sort of a drop based. Okay. But if you do it ECN instead of drop, then you get a similar results.
No.
Okay, maybe not. Need to look at it.
Test with ECN, right? The very beginning. But that was not.
Yeah, sort of way back on the ECN with LT and ECN with sort of a wireline bottlenecks as well. So, but the trick is how what kind of queuing delay do you trigger ECN mark, and that sort of you get the very different results.
I think everybody, it's Gori first. I think everybody's kind of said what I was going to say. I was going to say, let's make sure that our feedback's CE marks in a way we can use them flexibly as we discover what's going forward. And let's try and separate out this ECN stuff and get it moving quickly. But embedding lots of different variants of it in different places with different views of what ECN is doing is just making it more muddy and more opportunities for problems further down. So let's try and keep it separate, but keep the momentum going on it.
Jahed, I agree with Gori. I really do. I mean, I don't think like we should just try to figure out how the ECN marking should be done and how we should be reacting to that one. Maybe in later, when things are happening in the other working group, we have a clear view what to test. We can come back and have another test case, right? Draft.
Yeah, so it seems we have agreement that we keep it as a separate item for now. It's something that we definitely need to deal with, and we should have, I mean, we have it in the feedback, and the algorithms are also prepared to deal with it. So.
Should be discussed in the experimentation.
And we can also, yes, bring it up in the experimentation section, because this we have, so that we should make clear there.
Yeah, I mean, also make clear in the draft that this stuff is not well tested, so it's not recommended to use it as like the only base or whatever, but to really engage experimentation with it.
Yes, I was going to say this was actually the discussion about the wireless tests. From from what you sent, this draft was ready for reviewers. Is this correct?
Yes, I mean, I don't know, like we will get any update on the Wi-Fi test cases, but for the LT test case, I think it had been ready really last year. So, I mean, we decided to go only with eval test criteria not really focusing that much on wireless test case. And we said like when those who are interested in cellular networks and Wi-Fi network, they should run these test cases. Having said that, I don't say like other than us and NADA has shown some results on it. NADA shows on Wi-Fi network. We showed result on LTE network. So this is where it stands. I mean, it has been there. It needs some review from like the content perspective of like if there is any clarification needed and stuff like that. I have got some reviews. I have addressed this on the draft, but I don't know like what to do with this draft. What should you do with this draft?
Just a small update from NADA. So, so today we're not going to present results for wireless, but we're actively working in it. We are, as far as I know, there are no big issues with the tests themselves. We are more focusing on understanding what's going on with the algorithm, and yeah, there are Sergey presented some results in previous IETFs. So I think we have shown some preliminary results of how NADA is behaving on Wi-Fi. As I will say during my presentation, we didn't have the time or resources to go into cellular.
Okay, but you are not looking to update the wireless Wi-Fi part either then. So we are basically at the stage where we should need some more reviews of this document. Do we have some volunteers to review this? Yeah, of course, Mirja is saying we also would look for more implementations of the test cases, of course, for the other algorithms as well. But it would also be good to have a round of review of the document itself. So we have no volunteers at this time. Okay, we'll send a request on the list to see if we can find some people willing to review it. Okay, then we are at the valve test, and there we have, maybe you want to take those slides, Said, because there are some outstanding updates, outstanding questions on that.
Jahed, I mean, we for this eval test, we have gone through the reviews. I mean, there was quite a good of reviews, but now people are still experimenting with these test cases defined there. And recently we discovered like we have an issue. Ingemar raised it. Is like we have a short TCP model that creates some problem, and that saturates the whole path capacity. So there is really very little room for media to actually adapt. I mean, you actually go down to your minimum bit rate. That's what you have to do. So I think there is confusion on the document that we need to clarify, because this model that as I mentioned it, this model should go to the eval criteria. But I think Ingemar also tried with the eval criteria model, and it was like it's a bit better, but it saturates the network. Basically, the problem is like what exactly we would like to do with this test case. So in the next slide, if we have next slide, what should we do here? I mean, in the test case itself, it says like, okay, short TCP flow might appear as a long TCP flow, basically saturating your whole path capacity for time. But we have a separate test case for long TCP flow, competing with long TCP flow. So it makes sense to actually have some more realistic model for short TCP flows where actually the flows goes up, it's might saturate the link, and then it goes away and some, and then again you free up the capacity for your media traffic. Media traffic tries to adapt, and again you start to do something. So what is realistic TCP flow model? I mean, we have asked this question previously, and we was looking for input from our browser vendors because they have lots of data, but we got a reference to HTTP archive. I think the eval criteria model, it adapts the object size based on the HTTP archive statistics. But that's it. That's what we have. I mean, And then we can talk about solutions. We can, I think Ingemar and Varun going to present their experience with this test case. So maybe we should talk about the solution. What should we do here when they present on the later part of this
Yes,
meeting?
we have all the algorithm presentations. We'll talk about this test case,
Yeah.
so we can take that discussion again after that.
So my word of caution is like we should not do over engineering here, and we should not do engineering engineer the test case to make our candidate results look better. We should do what is realistic, and the realistic is, to me at least, short TCP flow might appear as a long TCP flow. So I don't know, like, and another option is we just remove this one because we cannot model a short TCP flow. So let's discuss it when we have time.
Okay. The last one that we have in the updates in this round is the GCC, and there has been a new draft, but it's mainly updating the text to clarify the algorithm that was already there. So it now has a section on the pacing mechanism, and it has a section about the pre-filtering. And there were also some details on this presented at the ANRW workshop that was held on Saturday. And the author's slide said you circulated that paper and slides, but I actually didn't see it on the list, right?
Gaetano Carlucci, I will send an email to the list with the paper and the slide.
Yeah, very good.
So I have one question.
Okay.
So on this draft, I mean, is it like I think this algorithm is implemented in Chrome browser, right? And is it like if I follow the draft and implement the draft in my simulator or in my browser or whatever application, will it be the same behavior? Will it show the same behavior in Chrome browser? Or is there any discrepancies between the implementation and what is written in the draft?
It's certainly supposed, Stefan Holmer. It's definitely supposed to be I don't know. I mean, I haven't implemented it based on the draft. I've written the draft based on the code. Obviously.
But that's usually why we try to get independent implementations, because you can check if you have the same behavior. As long as we don't have a second implementation, nobody can answer this question.
But that's kind of the state of it. But it's supposed to be the same.
And otherwise, the status of this draft is that the authors are still some parts of the algorithm that you are working on. And so you're looking to improve the loss-based controller and possibly consider some other improvements.
Right. So we are supposed to add a startup phase. That's something that's currently missing in the draft, but it's in the code. Okay, well, see future work. And we do have some work to do on the loss-based controller, as we have said. I think we also updated on that in Japan. So that's nothing new. We just haven't had the time to do it, but that's coming up.
Okay, thank you. But so for the next steps, this is the author's work to improve the algorithm and update the draft. Okay, so we move on in the agenda, and next is the feedback part. Said.
No, it's hello. Okay, right. Okay, so this is how the agenda looks like. I'll go through the recap of feedback requirements that we got from different candidate algorithms, but maybe I should say, like, well, this is an outcome. What I'm going to show here is the outcome of our design team. We formed a design team after the last IETF meeting, and we went through a couple of meetings. So this is a presentation on that one. So yes, so I'll talk about a bit what we did in the design team and talk about what we come up with, why we come up with such things, and then I think we'll go into feedback and overhead. That's basically Colin will say something. And then we have two versions of Word format of this proposal. I guess Vern will help me on that, two of that. And then we have some open issues we can discuss and what should we do now. So next. So this is a recap from last IETF meeting, and this is we have figured out okay different algorithms needs different kind of information, but at the end of the day you can actually merge them. There is a commonalities that you can actually use some information to get all the other information. So next one. Yeah. So what we did in the design team, we had 3 meetings, 2 with almost everybody in the design team involved, and 1 with 3 of us. So you see the meeting attendees, and we have written a draft on that with the proposal, and then the content of the draft will be discussed in the later slides, please. So this was the design team goal. I mean, the goal was like to go through the requirements, see like if there is any commonalities, and we can come up with a solution that actually enables interoperability. So when you have a sender implemented Scream, we have a central Scream implemented GCC, still they should be able to do some communication. Yes, and we also decided to do it for sender-based algorithm. That was also decided, like, let's do it for sender-based algorithm. So this is not, we didn't discuss the receiver-based algorithm in this design team. Yeah. So these are the information we thought like would be necessary. As you say, you need a packet identifier. Basically, it's the RTP sequence number. But there you can have RTP sequence number, you have SSRC and everything, so you can identify a packet. And the next information is actually packet arrival time. We'll call it later on in the format the packet arrival time offset. So when you get the packet arrival time and you know like which packet you're reporting on, you can do delay measurement, you can do digital measurement, and you can also figure out what packets have been lost. And also we need a specific marking of for ECN, and that's what I think we have already discussed. Like in the feedback message, we're thinking about incorporating ECN. And as you see, these are the packet information block. That would be one report on this could have like 1 or more of this block, and they will be grouped obviously with SSRC because still we're talking about RTP. And what we really need here is like what we analyze the already existing signaling mechanisms, and we figured out like, okay, we need a new one. So the new one will be reported as Excel block when it's a regular report. And if you need some frequent, if we need some frequent, I think that would be like frequency and overhead discussion will say like whether we need and more frequent than regular report or not. Then you report it as a like APPF feedback message. Next slide, please. So these are the design rationale why we need a new feedback message or an Excel block. As you can see, like this packet identifier, arrival time, and ECN marking. This is more like on the packet level. You don't get it on regular SSRC receiver report or sender report. So that's basically we cannot use that the existing 3550. And then we have Timben, but as defined in this 5104, it's not useful for sender base because what it requires really either you gather the information, you do your calculation at the receiver, sender recommendation or maximum bit rate to the sender, or you do it with some other means because you can send timber for different reasons, right? But that doesn't help the concept of sender-based adaptation. So we didn't thought like this would be useful. And we also analyzed the existing XR block. Yes, there are XR blocks to report delays. You have packet reception time, also 32-bit, and we have I think ECN for UDP that also has a XR block defined. You can report ECNs, and obviously you have lots of XR blocks actually reporting different sort of losses. So why do we need a new XR block? I think what we discovered is like, and I'd like to thank Ingemar, he did a good analysis on that one, is like we have some, you can combine the XR blocks. but we have some unnecessary headers, like XR block, you have a headers, right? And then you have duplicate information, like we have an in sequence, beginning sequence, in sequence, this kind of information is there. So our thinking is like, we can make a more compact version of XR block only for condition control feedback, and that should give more simplistic. And when I say more simplistic view of this feedback message is like the endpoints who is receiving it, easy to parse, easy to understand, and then in between on any SFU looking at it should be easier for them as well. Please.
Quick question, Jörg. I'm always feeling sort of unhappy when somebody says, we know what we are going to need, and let's just do this simple, concise representation of something. And next week you're going to find out, oh, well, dang, we missed something. So let's do version 1.5 of this thing. Let's do version 1.8 of this thing. So I'm not super convinced that this is a good idea.
Well, what we can definitely do, we can stack up different XR blocks and get partial information on all XR blocks and make and happy about that one. But that's where I think it's, but that comes with the overhead, right? But it's still, I mean, if we want to, I mean, all the experts are there in AVTX, so you go to there and ask like, if we are missing something, please tell us. But why?
I'm not saying that you know at the time of specification. Okay. The time you're done with the specification, the week after, we have gone through so many things where we had to deal with different versions and different protocols. People have implemented stuff again, different flavors of the spec, and always something has been missing. So one thing that I could envision that you might want to do is come up with an algorithm by means of which you would systematically extract parts of an arbitrary XR block that you could say, I'll put in these things, and you can compute the stuff and then have a rule set that condenses those to get rid of redundant information. But now crafting another packet format that captures part of this, then at the very least that you're going to have to do is deal with the new version of things that you are crafting and somebody sending a flavor of the old ones. So you have suddenly you get multiple different representations of the same thing. This just sounds like calling for trouble.
Well, I can say then, I mean, if I'm going to implement an algorithm which extract different information from different XR blocks to get this, and I don't know like why they are sent. I mean, is it for like condition control feedback or for something specific feedback? I don't know.
Colin Perkins. So I think what Jörg was suggesting was an RTCP extension or an XR extension to compress redundant information in compound RTCP packets. And yeah, we could clearly do that. That would perhaps even be a sensible thing to do, but it would be a very big change to the way RTCP is implemented. Now that's not crazy. You know, that's possibly even something we should look at.
You shouldn't be seeking everything.
Microphone, please.
I think we have a trade-off between doing the general thing and having a set of composable metrics, possibly then with an optimization scheme in RTCP, which in many ways is probably the right thing to do, but the overheads add up and we'd have to do all this optimization stuff, and that's more complexity and more time, or doing something that solves what we believe is needed for the congestion control problem with a relatively small overhead. I think, as we'll see when I talk later, that the overheads were already pretty big, and I think RTCP as currently specified, we couldn't realistically stack composable blocks to solve the problem we have today. My belief is that the time it would take and the extra complexity of re-architecting XR and RTCP to optimize that is probably not something we have time to do right now if we're going to get this deployed and into WebRTC, although it may be a sensible thing to do in the longer term.
Okay, yeah, that makes sense to me.
Yeah, Michael Romalo, I'd also like to agree with the comments that you could do better things and more optimum things, perhaps, by looking at what it is that we presently have. But the comment I'm here to address, Jörg, is effectively, Cisco has come full circle. We have something virtually identical to this that we did 4 years ago, and actually in development of NADA, and that is providing a recent history of all the timing of information on packets that were received. And in fact, we did that to develop the initial versions of our algorithm. So with regard to missing something and having another rev because we missed something that we needed for the algorithm, we're at least Cisco is fairly certain that we've got everything that's knowable on a packet that has in fact been received. So we don't think that we have that dimension. But you never know until you find that you really did miss something. But we're pretty confident there. I don't know what else on the other things that we could do to perhaps make it more parsimonious or more consistent with what it is that you already have. But that's obviously a possibility along with compression of the data. Thanks.
Yeah, I think the one data point I have here is the time series of the appearance of different XR blocks. Because we always we figured out that, oh, again, then we missed something. So let's do another XR block and do another one. So that's the one historic data point that I have for feedback information that we added and added on. So,
I mean, on that note, I think the primary objective was like, okay, let's make these 3 proposals that we have with Scream, NADA, and GCC interoperable. And then in the design team, we involve them so that we don't miss any information. So I'm not listening anybody saying like any proponent saying like we're missing something, we cannot do our congestion control based on this kind of feedback. So on that sense, we kind of main focus was like we should not miss something. We should not really need more than this. I hope we did a good job there, figuring out. But anyway, I think that's a reasonable way of thinking.
So Colin Perkins again. I mean, it's easy to think of things we don't have in here which could potentially be of interest for congestion control. Yes. I think we have to go with what we have for now. Maybe take this to AVT and have this longer discussion. Yes. And see what happens.
Okay, next slide. So feedback and frequency. I mean, we wanted to discuss this one obviously a bit. So if the general understanding is like the more frequent feedback you get, basically, you're more capable of reaction. I mean, you can react more quickly. But we have some limitations on our TCP bandwidth, right? It puts some upper limits how frequent you can do. But obviously, Colin has done some analysis, and so I think we'll see how frequently we can do, right? And then also overhead. But in design team we talked about a default value for interval, but we don't want to make this feedback as a heartbeat kind of thing. So and also a different algorithm has different requirements on intervals. So we didn't come up with, we didn't thought like this is a good idea to have a default value, but we can just say like, well, these are the range that where you can negotiate perhaps. So you set your session bandwidth in such a way that you actually get your desired interval report. That's the way of thinking right now. Next slide. So we have 2 versions. This is the first version. I think this was mainly designed for simplicity, that you have a fixed chunk of blocks per packet, and then you can parse it pretty easily. And then we have another version. This is a really new one. Vern, you want to say anything about it? It just the difference is like we took out this the loss indication bit, and we have an RLD there.
Yes, so in the side meeting yesterday, there was a discussion around like having larger arrival time offset. The third, I think earlier was 13 bits, now it's 14. And the resolution was 1 millisecond, and now it's 100 microseconds, which relatively means that you can only report on 1.6 seconds intervals at most. I think if you want more bits, we'll have to engineer. If the arrival time offset needs all the 16 bits, we'll have to come up with some more ingenuity. The question, I guess, the feedback that we want is, do we need all the 16 bits?
Magnus Weston, I think you're running up to another limit here because basically, I mean, assuming that we actually don't have path MTU much larger than 1280 or 1240 or something like that, you're actually getting into trouble here because, I mean, 1.8 seconds at even fairly standard bit rates is going to create larger RTCP report blocks than whatever is going to fit in your packet. So,
yeah. But you can, if you have a large RTP packets, I think you can chop it up into different several reports, right?
Yeah, but you should actually try to. I mean, yes, but it's really separate blocks. Why aren't you transmitting them more often? So, and then you don't need as much data in each. But so.
Varun again. I think the feedback that we're looking for is 1.6 seconds is okay. Like that's what I hear right now is that probably we can go even smaller. So could you go back one? Yes. So if we keep this,
0.8.
So then you get 0.8 seconds. So so the question is, if you're okay with 0.8 seconds reporting interval to be the max, we could just keep this one.
Yeah. I mean, these are two alternatives. We don't need to select anyone. We can discuss this and then perhaps, I mean, people can experiment a bit with both of them and select which is more effective.
Jörg, I was just going to say that I'm not aware that we would have actual rules on how you would split up RTCP packets, right? We have the rules on what we do with media packets because we thought those would be big. Now, if our RTCP packets also tend to get big, we should come up with something that defines timing and how you slice things in order to not leave people alone in those details.
I think it's better to, like, if you see like this is a really big, you split up into several reports, not like you split up RTCP packets into several packets.
Why would you do this? Just send regular reports more often.
Yes. Yeah. That's what.
Mosinati. So independent of the specific bits in this packet format, has the design team looked at how this feedback will interact with other feedback, or is the idea that most of the receivers would switch to completely ACK-based mode and suppress all traditional reporting like NAC-based reporting? Is there a thought about how this would you never NAC as a receiver anymore, and the sender would take the absence of ACKs in this feedback format as a retransmission request?
No.
So there's an expectation this is going to interact with current feedback as it exists.
Yeah, exactly. Yeah. So it interacts with like FIR. I mean, you can do it. It should interact with the timber. So we're not saying like this is very specific for condition control purpose. I mean, it should not really say like.
We're getting very far
else.
behind, so we're cutting the lines.
Okay, and so final comment on this packet format. It's useful to see ECN being echoed. I wonder if it may also be useful to echo more than just the ECN bits of the toss. There's plenty of applications where it's useful to know what transport level you're getting. And if DSCPs are getting through to the receiver, it may impact the sender's congestion control.
Jonathan Lennox, have all of the congestion algorithms looked at whether they work properly if you have loss on the feedback path?
Well, we have we have a test case called congestion on feedback path.
Okay.
People have been showing results, and we have seen some sort of resilience, delayed or lost feedback. Yes.
Okay. I have some more detailed questions, but we don't need to be for the line since we're behind.
Thank you.
Magnus Weston, to answer Mo, I think it's very important to actually separate this from saying this is just reporting on what's arrived, compared to semantics like I actually want you to retransmit this packet, because lost packet you might not actually want to be request them to be retransmitted. You're saying no, I'm gonna skip this packet, I ignore it, it's fine. So you need to have the actual semantics of saying I want this packet. So that's why you should use the different other feedback formats for doing that.
Yes.
So just echoing in response to Mo. Yeah, so this packet is a complementary to all the other packets that exist for RDP or RDCP, and the sender should not infer from this that they should retransmit or send an intraframe just because there was a burst packet.
Yeah, it doesn't have to. Yes. If somebody is smart enough to use this one, maybe yes, I don't know, but it doesn't have to. So we have some discussions on like, okay, whether there will be some guidelines this draft should say. How do you implement it? We said like no, perhaps no, but this is a job of this candidate algorithms. Like if they use these feedbacks and they want to know like how this timing information and is captured and what kind of how sensitive they are to those kind of information, and also like how frequently then they want this sender to receive or to report it back, they should have a consideration implementation section for condition control proposals.
Jonathan Lennox, I mean, the problem with this is that the person implementing the feedback and the person implementing the congestion are different implementations. So I feel like this needs to be not just implementation guidance, but actually what you actually need to negotiate in your, as you know, as your, you know, this actually has to be this isn't just an implementer guidance. This is you know, negotiation. You know, you know, I need to negotiate an RTCP fraction of at least this, RTCP bandwidth of at least this, or I'm going to fail the call because I can't do congestion control.
Right. So we have open issues like what clock to use for our report timestamp, because here you see like in the version 1 you have a report timestamp and then you report like how far the packets were received. So, but we need a clock to use. That's an open issue. Anybody has any suggestion? That we're open for that one. And what happens to the odd number of packets are reported? And of course, if anybody can help with the security section, I'll be really happy. But we already got some volunteer, right?
I mean, the one thing about the clock is the clock needs to be consistent across all the sources you're reporting on.
Yes.
Yeah. So you can't have, I mean, like for instance, you know, that's like the existing XR block. It's like, you know, that does arrival times. It's different for each clock, for each source, and that's not going to work. You need to be able to aggregate them.
I think so. If they're like multiplex on the same path, yes. Like one condition controller listening to all the messages. So way forward, agreed on the wire format. So let's, I think that would be an AVDX. So we'll update the draft, whatever comments we get, and push it to the AVDX. And should we continue the design team? That's my question.
And what is the feeling of the design team itself? You feel that you are near completion, or you need a few more meetings?
Let's hear from the members of this.
So I think, Colin Perkins, I think it's very clear that we need to continue the design team. We have a whole bunch of decisions to make about what timing resolution we need in these packets, what's the maximum duration of time we need to report on, how to configure things for the different congestion control algorithms and so on. So yeah, we've got some sketches of how we make, you know, we've decided on what information that needs to be reported, and we've got a sketch of how to do that, but there's a lot of details still to be fleshed out, clearly.
And also the draft currently has lots of design team related text, like this was like actually aiming to come here for Rmcat, but if it goes to AVDX, it should actually polish those kind of things, right?
Yeah, Michael Ramallah. Yeah, I think the design team ought to continue for the reasons Colin mentioned. I did want to address Mo's comment here, since we have some transport folks like Gori and whatnot in the room. I don't know that we explicitly thought about in the act of every packet whether or not to include the DSCP that it was received on. Of course, the sender might want to might keep track of what DHCP was sent on. So between Michael Wetzel or
if you get a packet identifier, don't you know that? Because you're sending it, you're classifying it.
But Michael's work and some of his Michael Wetzel's work and some of his graduate students say how sometimes that's remarked, right?
Yeah.
So it may not be received with the same mark that it was sent. So that's so my question to the transport guys in the room is that meaningful or not? So we didn't. I don't know if I consider it.
No, we didn't consider that one. No.
Jonathan Lennox, as the AVTX chair, I think if it were to come to AVTX, I would think we should have a design team there, which I would encourage to have exactly the same members. So I mean, I think this is something that needs that kind of concentrated expertise and the same people. So, I mean, I think the design team should continue whether or not it goes to AVTX. So you feel free to leave your notes into the design team.
But we already said, our last item meeting, we said that we publish this information in IETF group. So.
Yeah, we have.
Randall.
Okay, I think you should be on, Randall. No?
Yes. I agree. We absolutely should continue the design team. There's definitely a few more things to deal with, I'm not don't want to discuss it in any great detail here because but for example, whether or not there's any advantage in having the things like the amount of time and resolution of the timestamps and so forth be something that's negotiated. If there's anything that's worthwhile, effectively having externally negotiated or internally negotiated so that the feedback can be matched to what the congestion algorithm is looking for and needs, perhaps to avoid wasting a lot of bandwidth on something that a particular congestion algorithm doesn't need. This is one of the things we might want to talk about a little more before we're done here. But I think it's been very successful so far, and I think we need to continue it.
Okay, thank you. So I think the conclusion is clear. The design team continues.
Okay.
And Colin is up next, and we are behind the agenda. So let's try and keep short with both presentations and questions coming forward.
You used to have 10 minutes. Perfect.
Okay, good.
Time again.
So yeah, Colin Perkins. I'm going to be talking about how we do the feedback and the timing of the feedback. Next slide, please. Is this working, by the way? Okay. All right. So obviously we have a feedback loop here. We have the data being sent. We have the RTCP feedback coming back. Obviously, the dynamics of the congestion control depend on not only what information is coming back, which is what Zahed was talking about, but on how often it comes back and what the timing is. RTCP is the feedback channel for RTP-based applications. The question we need to ask here is therefore what feedback information can we provide and how often can we provide it within the constraints of RTCP? Next slide. So questions we need to ask, right? How often do we need the feedback to make the congestion control work? How much overhead is acceptable? Because obviously the more feedback information you provide, the more cost there is in doing that. And what information do we need to feed back in each report? And sorry, previous slide, please. And then how often, and that then turns into how often can we send it in RTCP, and is that suitable for what we're doing? The takeaway is, if you take nothing else from the rest of this talk, we probably cannot give per packet feedback in RTCP. The overheads are just too much. We almost certainly can do feedback per video frame. And I'm going to walk through the analysis that shows a very initial analysis that shows how that is feasible. If you want to do feedback per round trip time, yes, probably, provided the round trip time is not time. And I think what probably makes most sense is to do feedback for every video frame. Next slide. So feedback in RTCP, there are basically 4 types of feedback you can use. You can do the regular RTCP reports, as in RFC 3550, your sender reports, receiver reports, and so on. Possibly with XR block extensions. We can use the AVPF feedback either to get NAC-based feedback or to just because it allows shorter reporting intervals than regular 3550 feedback. We can aggregate RTCP reports from different SSRCs into a single packet to reduce the UDP header overheads. And we've got the reporting groups extension, which we did in AVT fairly recently, which allows you to suppress unnecessary reports from multiple co-located SSRCs. The reporting groups is optional in the WebRTC RTP usage. All the rest are things which it says that you should do, although I would be surprised if anyone actually implements the aggregation, although it's been in there since 3550 with some more recent clarifications. I'm assuming the XR block that Zahed spoke about is being used. The analysis I'm going to talk about was done using version 1 of that block, which is the version that's in the draft. Okay, next slide. So example scenario. We're doing a point-to-point video conference, 2 people, each with audio and video streams being exchanged. That means there are 4 SSRCs, 1 audio SSRC and 1 video SSRC from each party in the call. We're assuming everything is bundled together, so everything is going on a single 5-tuple. So the source is sending audio and video streams with their own SSRCs, and it's receiving an audio and a video stream also with their own SSRCs. The analysis I'm trying to do is, can we do a congestion report of every video frame using standard RTCP mechanisms? Next slide. So first of all, we assume that the senders are aggregating their reports. So it's arranged it such that the RTCP packet for the audio SSRC and the RTCP packet for the video SSRC are sent together in a single UDP packet. And RFC 3550 said you could do that, but didn't give any details in how to do it. And the RTP multi-stream draft we did in AVT, which is currently with the RFC editor, fleshes that analysis out and tells you how to actually go about doing that without messing up the timing rules. So the reports from 2 SSRCs are put together into a single packet. We're also assuming RTCP reporting groups are used. What that means is that one SSRC acts as the reporter for the endpoint, and the other one delegates its reports to that. So rather than both SSRCs, both the audio and the video SSRC, sending reports to say they received all of the packets, one of them just says, my performance, my reception was the same as that one. I just use that report. So it's a way of reducing the overheads. Yes. Since we're aggregating the reports, it doesn't actually matter which one of the SSRCs acts as the reporting SSRC and which one delegates it. The assumption in all of these slides is that it's the video SSRC which sends the reports, because it's more likely that that will also be sending NAC feedback and interframe requests and that sort of thing. But it doesn't actually matter which one you pick for this analysis. Next slide. So what's in the compound packets that get aggregated? Well, for the non-reporting SSRC, it's pretty straightforward. Right? There's a sender reports packet, which has the sender info block, which has the information you need to do lip sync in it. There are no reception report blocks in there because it delegated it to the other SSRC. There's an SDES packet with a CNAME in it, and there's the RGRS packet, which is the bit of the reporting groups format which says, I'm the non-reporting SSRC, go see the other one. If you add those up, it's a little hard to see the slides from here. I think that was 28 octets for each of the first 2 and 12 octets for the other one. If you look at the next slide, please. If you look at the reporting SSRC, things get a bit more complicated. You have a sender report. That will have 2 report blocks in it, one for each of the remote audio and video SSRCs. Right. That I think it's 76 octets when you add all of that up. So there's the sender info block and the 2 report blocks. There's an SDES packet in there, which has the CNAME for the video SSRC and has the RGroup identifier for the reporting groups. The RGroup identifier is specified in the reporting groups draft as being formatted like a CNAME. So essentially, you're sending the same CNAME twice. So there's an obvious optimization there, which is send a much shorter identifier for the reporting group. And there's nothing in the reporting group spec that says you can't do that. Well, there's nothing in the reporting group spec that would break if you did that, although it says you shouldn't. So maybe we should revise that before it goes to the RFC editor. We're also assuming that there's then the XR block, which Zahed talked about, which contains the congestion control feedback in this packet. The header for that is 32 octets when you add, when you look at the XR header and all of the other information. And then for each audio packet received, there are 2 octets, and then there are 2 octets for each video packet received. So if you add all of that up, and you add in the SRTP authentication tag, and you add in the UDP header overhead and so on, you find the report is 266 bytes, plus 2 bytes for each audio packet received, plus 2 bytes for each video packet received. Next slide. How many audio packets and video packets are received? Well, I did the most dumb, simple thing I could do to get the analysis done, which is assume CBR video and just assume that everything is evenly spaced. And that's not the right thing to do. We all know that, but it gets some numbers to see where we're going. I also assume that audio is just sent 50 packets per second. And yeah, okay, this needs revising, but it's a good place to start. Next slide. What does that give you for a reporting interval? Well, if you troll through RFC 3550 and through, I forget the number, the AVPF, RFC, all of the RTCP timing rules boil down to the reporting interval is the average RTCP packet size multiplied by the number of SSRCs divided by the bandwidth allocated. In this scenario, there are 4 SSRCs, 1 audio, 1 video for each of the parties. The average RTCP packet size is the value I just calculated on the previous slides. The bandwidth, we're assuming 5% of the session bandwidth. And because we're aggregating, you have the average RTCP packet size, and the rationale for that is in the multi-stream draft. You run through all of these numbers, next slide, and you know, the calculation, I don't expect you to read it, it's all in the draft. What it works out as is if you're sending more than about 2.5 megabits per second, then you can report on every frame of 30 frame per second video. Next slide. So that's the headline conclusion, and you can work through the maths in the draft if you care, and obviously we can refine this analysis. There are obvious ways of optimizing this. We can optimize the reporting, the congestion control feedback reports. We can clearly optimize the reporting group extensions. It's all very preliminary analysis. If we believe 30 frames per second at 2.5 megabits is plausible with 5% overhead, then we can do this. We can plug in different numbers and rerun the analysis. And if you have any favorite operating rates in terms of bandwidths and number of SSRCs and video frame rates and so on, send me what you're using and I'll run some numbers and we'll see if this works out.
Varun Singh. So I think the 5% means that you can't send anything else. If you do this math and that you come up with the number, that means you can't send the NACs and you can't send anything else that you might want to.
Well, I mean, the NACs you'd be using the AVPF feedback, which means you can, I mean, you would slightly increase the rate because you'd be sending early with a NAC, but I think you'd probably get away with it without increasing that a whole lot. So,
okay.
So as long as you don't want to send NACs too often, I think you'd be fine.
So it's like fears, and there are so many other messages that are going back and forth, and so that need.
And I think it depends how often people want to send those. If those are occasional things to indicate a problem, then I think this is fine. If these are things that are sent regularly, then we'd need to figure out how often that was done and include that in the analysis.
Yeah. Plus, there are other XR blocks that people might want to send. Yeah. So this is really limiting if you take all the 5%. So if you're really close to like per frame.
Yeah, sure. And what we need to do is think about, are people doing anything in addition to this? Are they sending over feedback, over XR blocks, NACs, and so on? How often are they doing it? And then just rerun all the numbers. And
yeah.
I know you suggested by emails people send an extra stream for screen sharing, which should be included. And there's a whole bunch of things like this.
Exactly.
Yeah.
So we're getting very late, so try to be very short, and then we can continue this discussion on the mailing list and in the RVTX as well.
Jonathan, yeah, I mean, I think 2.5 megabits is a fine operating mode, but there are plenty of very real operating modes much lower than that. I mean, I think that, we're gonna, one of the cases is, we want to figure out if we can go from audio only to audio plus video, which means we're probably starting at like, tens of kilobits per second.
Sure.
And, I think that as described here, that would mean feedback every 3 seconds, which is completely implausible. So.
Sure. Yeah, I mean,
so
I think that what I want is people to tell me what operating modes they use.
Right.
And we can do some analysis and see if it works.
Okay. Yeah. I mean, we can talk offline. But.
Mosinati, thank you for the analysis, because it raises an immediate red flag for me. I'd go beyond Jonathan said, and so this is, we're orders of magnitude beyond what we need to be. We need to have, very good reporting at much lower order of magnitude, lower bit rates.
Sure.
And one other problem I think is that in the feedback formats that were proposed, if you model loss as part of your design here, I think you'll find dramatically worse numbers, because the feedback format is assuming contiguous sequence numbers on the AX. So if you had discontiguous blocks of if you had a loss in the middle, you'd have to report the starting and ending sequence multiple times, right?
No.
I didn't see a bitmap of what was lost and what was not.
So-
It's a per packet feedback.
Let's continue this discussion offline. Okay.
That's not true. It's more optimized than that.
Okay, but it would be good to add loss as part of this modeling to see what does the feedback
But
rate really
it
become.
doesn't affect it, the way the feedback format's currently defined.
Okay,
Yeah, it reports losses. Yeah.
okay, that's good.
Yeah. But yeah, please do send me the operating modes you use, and then I will run some numbers and we can do this, and we can do this based on some real data.
Okay, thank you. Then we move on to the framework document. Then if we can be very quick, this will be good because it's a short document.
Okay, that's good. But anyway, I really wanted to discuss this, if this is an useful thing that we should continue to doing. So the idea was like, okay, we started with some interaction app draft, then we split it up 3 drafts, framework draft, app interaction, codec condition control interaction draft, and stuff like that. And the goal here is to, okay, or the motivation is to, well, in all the 3 different proposals, we use different kind of terminology to actually kind of describe same kind of functionality. So what do we do? I mean, can we make a kind of framework document where we can describe all the modules with a given name, so that these condition control algorithms could actually describe their own solution on using this terminology, and people actually start to read this framework document, the developers also, implementers also kind of get an idea like what exactly the functionality and the modules we're talking about here. So that's the idea. Let's move on to the next. So we come up with a couple of modules. We give it a name, but obviously any suggestion on changing name or change on description would be really helpful. So the first one is linear condition controller. So they basically it detects an available bandwidth based on your RTCP reports or the condition control feedback, any kind of feedback. And then basically you have a transmission queue, because we also realize that if you have a bandwidth and you have a rate recommendation, your video coder can overshoot, undershoot. So you need some sort of pacing here. So that's basically a transmission queue.
Varun Singh. I think when I read the document, I had a feeling that it's not following the RDP taxonomy. I would suggest that you actually do that rigorously.
We didn't run through the RDP taxonomy right now.
Because there was some confusion. Like, for example, I had a question, or I have a question related to the fact that does the congestion control run on a specific 5-tuple, or what happens when RTP and RDCP gets non-masked, and if there is unbundled scenarios, or if there are multiple transports, what is the expectation? Does the congestion control run over each 5-tuple if you have multiple
I think
of those?
the description should say like it runs on 5 tuples, but it should include like what happens when you multiplex it. So it should cover both. But the basic assumption when we would try to text it, so say like, okay, let's work for single stream 5 tuple and then go for aggregation.
So my feedback, since I want to be very quick, is the fact that it's a very good start for a document, but it needs to be a bit more rigorous in the deployments or where you see congestion control moving. Especially, we've seen different types of deployments of these streams, and there are various scenarios for people to do that. And it would be nice to cover that in this document, because this is indeed a framework document.
Yes, I mean, exactly, that's the essence. I mean, the framework document should define all the modules and terminology, and then how do you combine them? I mean, we have two examples in the document saying like, this is for single stream, this is for multiple stream. How do you combine and how to use them is actually, I mean, the condition control algorithm, they deploy different kind of
that's why I said the taxonomy is important, because when you say the stream, I'm not really sure you're talking about an RDP stream, or are you talking about like an ICE transport?
So basically, the thing is like the effort on that one is not that aggressive from our side, because we didn't know like if we're targeting a real issue or not. Should we continue? If we continue, we definitely need to go through the taxonomy. So next slide. Next slide. Oh, 2 slides back. So you have a red controller. Basically, what it does, it gets feedback from it gets the estimation from the network condition controller. Then you have a transmission queue, pushing it back, like giving it queue length and everything. Then you have a shared state where basically this couple condition control comes into play. Like what is my maximum limit here? How do you distribute multiple priorities on stuff like that, or multiple, for example, data channel versus media channel and WebRTC. It takes all the information and have a red suggestion to the video encoder. And then we have a network probe generator, because we also have kind of thought of this kind of scenario where you would like to probe the network when you're going up. Like we have a suggestion here is like FEC based condition control, where you can use that FEC to actually probe the network and see like what you can actually send. And then we have a shared state module. Basically, it says like, okay, if you have something called couple condition control, you can have an exchange kind of scenario where you actually cross-check. Well, this is my estimation. This is, I think, what I send. Is there anybody using the same path or same bottleneck, sharing the bottleneck on the path, gonna affect on that one or have any say on my current estimation? So those kind of things there. So in the draft, we now have two configurations, one for single stream and one for multiple stream. This is how it looks like. I don't know. I was planning to actually go through all of this, but I don't think we have time. But we have an example on single stream, and then we have an example on multiple stream. Please go through the document, see like this is the interactions we are talking about, and see like if we can, the existing candidates can actually reflect to this one. I mean, can they map to this kind of arrangement, or if they cannot map. I mean, this is not a fixed arrangement. The document says like this is an example. So if you have a different arrangement of the same modules, please let us know.
Varun Singh. So my main question was that this is a simplification, and this is what we all want for WebRTC, but or for RTP. But there are scenarios where the encoder 1 and the encoder 2 go on two different transports. Yeah, and the guidance that I was looking from in the document is to say if the congestion control would run over those two or would run independently for those two. And I think that's something.
Is this a framework document should say that? Or
I think it should
like,
either limit the scope to say that it's only going to say like everything that goes over a single transport, or what happens if things go.
This is what I said. I mean, we're working on some single transport 5 people. And then if you want to multiplex, you can multiplex like this one, or you can run separate condition per.
So I think it should definitely say if that is the thing that you want.
Okay.
Then you need to clarify that.
Yeah, we need to clarify that one. Yes. So next. So we basically need inputs. I mean, is this a good start? I think Varun said it's a good start. And is it something useful, something that people want to use? Then we will continue, go through rigorous update and otherwise, I mean, I don't know, like, what should we do? And basically, it was a requested document from the working group. So I don't know, like, if we should bring it at a working group item or continue as an individual. Because it is not supposed to be an individual. It is supposed to be a working group thing.
Varun Singh again. I think it needs some work. It doesn't matter if it's taken as a working group or stays individual. It can progress. Since we wanted it, it's good to have it. One further thing I wanted to know is should the output of this document be used by the other proponents to like realign their architectures and terminology?
Yes.
Assuming the terminology in this goes.
That is exactly the mission here. So they need to do that.
Thank you.
So that's why this document is actually important to actually progress it really fast so that we can move on with the candidate.
Yes. Jörg, just one quick comment. We had a similar meta discussion yesterday morning in the electoral networking research working group. Okay. And so I think the document is very useful, and we should be continuing working on it. I would like to leave at this point open what the final stage of this is going to be. To me, these kind of modeling things are usually intellectual exercises where you learn something, but you don't know how you're going to use what you have learned in the end. So I wouldn't want to make a promise that this is going to be a whatever RFC, the document that's going to be referenced by everything, or whether this has just been, is just an assistance thing for us in the process.
Yeah,
so
I mean,
I just like to be a bit vague on the
yeah,
final.
Okay, I understand that. I think the idea here is like if it becomes something that is everybody using as useful, maybe it becomes some sort of like a reference. But if it doesn't do that kind of thing, if we cannot converge to something that is useful, it might be an educational thing. Yeah. Exactly. Yeah.
So now the chair is looking for something, input or?
I mean, another question, like we also need to think about the relation of app interaction, codec interaction to this one.
So I think if we just delay the adoption call and just say that we fix the terminology first and see like how it looks after the terminology fix and everything's like consistent, then we could consider it. After that.
Actually, I was actually going to ask the chair, like, should we really submit as a working group item from day one? But
So this is clearly a document that the working group has asked for, and we have now the first version. So I guess the question we will ask the room is if you are ready to adopt it now, or if you would like to. So my first question will be, would you like to adopt this document as a working group item in its current state? Or the second option, would you like to have another update by the authors based on the feedback that has been received? So if you would like to adopt the document as a working group item now, please hum. If you would like to have another update by the authors first to take feedback into account, please hum.
great. So that also means like I'm going to get lots of input from you guys. Just don't shut your door. Yeah.
No, we clearly need the working group to provide input for that update, and we would urge all the candidate authors to read the framework document and let Varun know if this, is aligned with what you're thinking. And sorry, Said.
So I mean, the idea is like we update it and call for adoption later on, or we update it and submit as a working group item now.
No, we update it and then we make the call for adoption. Okay, we move on. And it's the traffic models.
When you do hum, it's good to repeat what the result of the hum were on the mic so that people can understand.
Ready?
Yes.
Hello. So, good morning. My name is Sergio Mena. I'm going to present the updates on the video traffic source draft. It's joint work with Xiaoqing and Zahid, who's here. So the outline is very simple. What's new? So what we did new there and what's next. Then with the what's new, which is actually the meat of this presentation, I'm going to present updates on three fronts: the draft, the video traces, and the open source code that we have called Syncodex, and then a few plots for demoing. So updates to the draft, we have focused on section 7, so the draft didn't change significantly, only on section 7. So before these updates, so by Buenos Aires time, so we had a comparison of both models in that section. So, stressing what good parts and what advantages and inconvenience had these two models. We have now turned that into a set of guidelines on how to combine those models to get best of both worlds. So, just a quick recap. Actually, we don't have the time for this, so I'll just spend 10 seconds just to remind that there is like the statistics-based model and the trace-driven model. This is like the two parts of the draft. And next, and so back to section 7. This is what we're proposing to do. It was clear for a long time that the statistics-based model is better at representing transients, which we call the transient state, and the trace-based model is better at representing steady state. So what we're doing here, this is just notation from the draft. So I put a new target right coming from the controller. We make the decision whether there is a 20% increase in the rate or not from the last time we observed that. If that is the case, then we consider ourselves in transient mode, and so we go by the rules of the first half of the draft, which is the statistics-based model. Because this is a transient state, we do that again for the next the next case of the frames. That's what the statistics model mandates. On the other branch, so if we see that the increase is not reaching 120%, then we just keep on, getting the frame sizes according to the trace and the rules of the trace frame model. Now, the 20% increase here, we have chosen that value following our experiments that Xiaoqing extensively presented in Buenos Aires. So we are actually, as we speak, there is an ongoing effort for using the Mozilla Codex. Thanks, Randall, for the help. And so we are, of course, willing to modify or to complete any of these values if the results from this study diverges from what we got from X264. There was a little bit of controversy last time why we had used X264 and how often this is used for live streaming. So that's what that's the way that we are addressing that concern. So that's for the draft. Now let me just say a few words on the video traces. So the video traces is like remember, it's the fuel on which the trace frame model runs, right? So here, like the news I would like to convey is that our quest for the right video trace continues. We haven't found it yet. The problem is that the requirements we have are quite stringent. So we need at least one minimum of trace. So this is fairly big for a test sequence. We want a fairly high resolution because we have to, when we go offline, we encode at several resolutions. So the initial resolution should be at least the maximum one we're going at. And it should be like a talking head like content. So there should be very few, if any, scene cuts in the sequence. Now, what we had by Buenos Aires was two sets of traces. So there was like a set of short ones which had the right content, and then we had longer traces that were like that's what we could find. So it was animations. There were some suggestions in the last meeting. We went to those places that people pointed to, and unfortunately we didn't find those traces. So we're still looking for it. We're also considering, we didn't have time to do it, just that. We consider producing them ourselves because of the lack of time and because this was somehow blocking the yes, Mo.
Mosinati, so we can give you more sequences for a head and shoulder video conferencing content if you want. NetVC has a repository of plenty of sequences.
Do you have like, because it's jigs, I mean, you realize the uncompressed size of what we want is like jigs, tens of jigs.
Yeah, we have
them?
I think over 50 gig of,
that would be awesome.
of sequences up
Can we
there.
talk later?
Yeah.
Thank you. Anyway, so for the moment, we didn't want to block the study on NADA. So what we did was we took a pragmatic approach, which was the short sequences we have, which are the right content, but they were too short. We're stitching them together. And this is what I'm going to explain briefly in the next few slides. So this is just a reference slide. This is what the video traces are coming from. This has been like that for a long time. Please, next one. So what did we do? We took any sequence, just took this one. It could have been any other one. And for the second and third sequence, we removed the first 55 frames, because 25 frames, sorry, because those are the intracode frame, initial intracode frame, followed by the smaller V frames. This got us from like 3 sequences that amount for 10 seconds to 32 seconds. This is still far away from the 1 minute that we think it's best, but way better. And the result of this stitching, we added it as a new sequence called CountCat. So this is just a graphical explanation of what I just said. So these are the three sequences. That's how it looked like. Just for the next presentation, look at how the frame sizes. So on the x-axis of is time, and on the y-axis is the size of the frame. So you can look at, of course, there are 3 different talking head-like sequences, but 3 different. You can see how noisy the output is. This is going to be important to explain some things that are coming up in the next presentation. This is the resulting sequence. I apologize. I've used copy pasting on Octave, and it's kind of cut because it's the same. The x-axis is the same. So sorry about that. But basically, you can imagine how it looks like from the previous slide. We just had a look at the histograms of the 3 sequences and the resulting one. We removed the first 25 frames on each of these because what we wanted to analyze here was the steady state behavior. And basically, the message of this slide is that we had presented this in I remember in Prague. The thing here is that somewhat not surprisingly, the distribution of the sizes of the frames for the concatenated sequence is not fundamentally different from the three original ones. Okay, so that's all for the traces. Now on the open source implementation of the models that are described in the draft. So a very small recap what it is. So SyncCodex is a set of C++ classes, very easy to use. They are platform independent. You can use it on your favorite simulation framework, even in real test beds with no change at all. They're very easy to use. The update here is that we added a new codec. The traffic source, we call it codec in the C++ code. So that implements simple video content sharing, and this is based on a discussion on the mailing list that was a little bit after Buenos Aires. There were some people from several organizations involved. So what we did is just we took the results of that discussion and we implemented it as a codec. Just a few words what it is. So this is trying to model the, somebody sharing slides, sharing content. So there are very small frames that basically say no op, just keep on showing the same content. And at a given point, when you transition on slide, there is a huge transition frame that is like, these are like between 20 and 200 times the size of the no-op frames. And these are the default parameters that people seem to agree on in the list. And of course, in the code, you can change them if you want to do some other things. Now, some small plots to demo what I just explained before. So this is a perfect codec. So just a reminder, what we call perfect codec is like the most simplistic way of modeling traffic video source. You perfectly conform to what the congestion controller is asking you, and you do it instantly. Okay. Speed up. Okay. So this is the base. So here the graph looks very nice because there is no noise coming from the video traffic source. Next one, please. Here, this is the situation with simple content sharing codec. Okay, so this is this new codec we have added, and this is how it looks like. So you can see there are lots of spikes in the receiving rate on the first part. Those spikes are also reflected in the delay, the one-way delay that we perceive. And well, in this case, that was a tuned version of NADA, but it could be any congestion controller. You can see that also it incurs losses at some points. I'm going to further talk about this later in the other presentation. And finally, the last plot. Can we advance?
This was, yeah, that is already.
Was it this last one? There was this one. Yeah, thank you. So this is also a way to demo this concat sequence that we have been working on in order to be able to try it on our algorithm. So as you can see, very briefly, we're going to talk about this later. You can see how noisy the receiving rate is, and also this noise is also reflected in the delay. There are some spikes in the delay here and there. In this case, for instance, it didn't reach it didn't fill the bottleneck queue, so there are no losses. But basically, this is what you face when you are using. So of course, this is noisier. This is harder to explain. This is not as nice as the first of the plots, but this is, we believe, closer to reality than the other one is. Now, what's next? So the next steps is we would like to implement the hybrid model, the one I just explained, the updated section 7 with. We'd like to implement it in our open source in our open source family of C++ codecs, as we call them. We would find video sequences, so thanks Bob for intervening. We have to sync up just after the meeting, so that we can actually use, rather than stitching them together, we can use the right sequence. We would like to further the study on the transient behavior. I just mentioned it before. There's an ongoing effort with Randall. Once again, thanks Randall. And then, can you guys, just the last thing, just to mention it, I don't remember it by heart. Come back, just the last bullet. Thank you. Yeah, and then we would like to have feedback from you guys. If you happen to use the SyncCodex, we would be very interested in seeing what works, what doesn't work, what would you modify, what would you remove, etc. Thank you. That's it.
Okay. Thank you. And you have the next presentation as well. So
yeah. Good. So let's switch gears a little bit. So we're going to present. So we've been presenting performance results for NADA for quite some meetings now. This is just a small updates on the wired test cases, which are more mature. So this next one. So this is the outline. So first of all, I'm going to explain where we are in terms of the evaluation, like the big picture. Then some plots, which is such a sample results, interesting results for the wired network test cases. And finally, summarize and say what we're going to do next. So this table explains our progress in evaluating NADA. So the columns are the test suites. So the first column is the wired test cases, according to the draft. Then there is the wireless, which are divided into Wi-Fi and cellular. This is what's specified in the drafts. The rows are, first row is the perfect codec, so no noise in terms of the video source. And then the different flavors that I explained in the previous presentation, and it's displayed, they explain in the traffic source draft, the different kinds of, the main kinds of video source that we are considering. Now the axis means what we have run and are running and are evaluating on NS3, and the red square is what we did in NS2. We are using two frameworks. Well, first of all, because of the way we had to work and we had to advance, but it is handy to kind of validate the results. We will see in the plots that we took the time to see if the two different implementations, different simulators, match or match or don't match. This is a caveat slide. So even if we implement in both simulators, the implementation is exactly the same. So for instance, in terms of the algorithm, there are some aspects of the algorithm, for instance, the initial ramp-up phase, that are sort of simplified in NS3, and they are implemented according to the draft in NS2. The reason of this is not laziness, is because of the internal history of how the NS3 effort started within Cisco, which was comparing some other in-house commission controllers. So the interface was already defined, and we couldn't change it. And so there are some data, for instance, RTT data, that is not available there, so we had to simplify it in NS3. Off the record, we are now undergoing an effort of revamping the NS3 implementation that would be completely independent from any other effort within the company, and we have full control on what we want to do with the interface and other. Actually, that's an excellent opportunity to follow the what will be decided on the framework and interactions draft. That will be an excellent opportunity to try that. And I cannot promise anything, but we might be able to. In a future, now we have progress, but there's a lot to do. We might open source it as we did with Sync Codec, so that people could actually use that to implement their algorithms in a simulator, a common setup, with all the code reflecting all the ideas that have been prescribed in the different drafts, and having a perfectly fair comparison, even if it's just a simulator. So this slide is, so I'm going to focus now on just some sample of the results. I'm focusing wired. The wireless effort is ongoing, but for the moment this is like the more mature. So those are the results we wanted to present. So this is the whole lot of test cases we have, and the things in bold are the ones I'm going to focus on. This is just a sample. We run all of them, but I'm only presenting the bold ones. So let's start simple. So let's take the simplest case, 5.1, and let's take the simplest traffic source, which is the one that is perfectly conforming to what the controller is asking. So the goal of this exercise, of this slide, is compare the results we obtain with NS2 and NS3. And you can see that the behavior more or less matches. Don't get confused by the orange part of the left, because this is actually the UDP rate. This is back on the discussion on, so this is like the version of 5.1 where we're using background traffic. But you can see that if you just focus on the blue line on the left, it's in terms of rate, so it actually matches what you see on the right. Also, it's very obvious in the delay. The only main difference you might observe is that the line is thicker on the left. This is because in NS2, that was in the other slide, I didn't present it. In NS2, we have the Newton model that is included in the, I think it's the eval test or the test cases draft. Whereas in NS3, we didn't implement it yet. This is something we have to do. So that's why the line is thicker. Now let's focus now on NS3, and let's stress a little bit the algorithm using less trivial traffic sources. So on the left hand side, you can see the the trace-based, and this is using the new concat sequence that I explained in the previous presentation. As you can see, the output is noisy in terms of receive rate. So if you see the orange plot and on the first third of the left part, you can see that how noisy the receive rate is, because remember when I plotted the sequences themselves, it was really noisy. I mean, from in a very few frames, you could change the size of the frame. You could change dramatically. So you're seeing there. Then so the blue line, which is the bandwidth estimation that NADA is doing, is actually smoothing that out. And you see that, well, of course, there are some valleys here and there, but the algorithm is working. Now, because of these irregular frame sizes, you can see some impact also on the delay. The only exception is the peak that you see at second 60. This is not because of the source. This is because of the test case. That's where the test case says that the capacity dramatically decreases, and so that peak there is because of that. So NADA is really adapting to changes in the environment, is not trying to deal with the noise that is coming from the traffic source. And then on the right-hand side, I won't spend much. This is really preliminary. This is the first results we're getting from this content sharing traffic source. This is the most stressful for the congestion controller that you can do so far, okay? Because you have the rate is very low, and at times you can see it spikes. You can see it on the receiving first third on the receiving rate, the orange plot, and also on the delays. In this case, actually, so we see actually here the two observations are that NADA, even if it's very spiky in terms of receive rate where you're sending, so you can see the mismatch between the blue line, which is what NADA is asking, and the orange line, okay, which is what the traffic source is giving you. It's really, there's a real mismatch. And even like that, you can see that NADA is sort of, is not going overshooting or undershooting, breaking down. It's like, sort of stable. And then on the bad news part, if you see the losses, which is the third one, you see that we are experiencing some losses. So this is, even if there are not many, this is not really a good thing to have. And we diagnosed that, and we are convinced that this is because the NS3, this is in the previous slide, so the NS3 implementation is lacking this right shaping buffer that also was discussed in the framework. I don't remember now the terminology, but we are missing that in NS3. We have it in NS2, but we're missing it in NS3, and that's why we have the losses, because the network itself couldn't absorb those bars. But we believe that those will be fixed when we implement this. So the message is, these losses are not because of a flaw in the algorithm. It is rather because of a gap in the implementation. Okay, so in 5.4, remember three Rmcat flows sharing the same bottleneck. So again, we go down to the trivial traffic source. We see that the behavior roughly matches. You can see that the delay is more noisy. Again, it's because of the jitter delay that is not implemented yet in M3, and basically the behavior in the rate seems to be quite similar. It's a bit more noisy in the NS2 case because of the jitter, we believe. Now, same test case. I'm now presenting, like we're now plugging into the system like the trace base as before, as with 5.1, and the content sharing. So for trace base, you see the thing is very noisy, very, very noisy, both in terms of delay and in terms of the rate. It's really varying a lot for the three flows. But the two observations here is, one, that NADA doesn't break down. Like if you see the long term, it's like more or less oscillating, over the same rate. And if you can visually appreciate that the mix up in the colors there means that the fairness is preserved even under those noisy conditions. There are no losses. Then for the content sharing codec, you see that things get spooky. So the rates, again, the algorithm doesn't break down. There is a first phase where the rate is a bit bigger than later on, and the reason is because of the losses. You can see that the loss, because of the randomness of the model, there are more losses towards the end. So that's why. Again, this is even if I could tell you that NADA doesn't break, that it does what it's doing, we find this is not acceptable, because basically the quality of experience for a user using these flows with those losses at key moments where you're transitioning your slide wouldn't be, this is, in terms of quality of experience, would be poor. So we are working on, the first thing I would like to say again, the first thing we need to do is to implement that right shaping buffer to see how it reduces those losses, because, this is something we have to work on. And finally, 5.6, remember, is our Rmcat flow with a long-lived TCP flow, sharing coexisting in the same bottleneck. Again, we use the trivial traffic source to compare them, and you can see that the behavior matches. So the most obvious one is in the delay, so the middle plot. You can see it's matching, and again, the line is thicker on the left because the jitter model is implemented in S2 and not in S3. For the rate, you can see, don't get confused. So the orange plot on the left is the TCP rate. So you can see how it's fairly fair with, the two flows are fairly sharing the bandwidth. So if you focus on the blue on the left, first one, like the rate, if you focus on the blue and you compare it to the ones on the right, which are basically sending a receiving rate, you can see that the behavior matches. In terms of the losses, so in terms of the losses, you see that the losses are governed by TCP. The loss events, they actually happen at the time where the sawtooth, the TCP sawtooth reaches the peak. The difference in the two, like in terms of, there's no difference, how to say this, there's no real difference between the losses on the right and on the left. It's just that the scale of the plot is changed. So you see that it reaches 35 on the left, and it's only, I think, 8 on the 5. So it's 5 times. So that's why, I mean, it's actually the same, approximately the same. It's just a scale, a problem in the scale. And then, like, here's when things can get a little bit harder. So again, same test case. So remember, there's a TCP flow there, and then there are non-trivial traffic sources. So for the trace base, you can see that the rate still gets noisy because of it, and still NADA is able to somehow smooth it out in terms of the bandwidth it is estimating. In the delay, you can still see the sawtooth from TCP, but now it's a little bit like degraded because what the flow is doing is sending frames of irregular sizes. And nevertheless, the losses are still governed by TCP, so we don't seem to be introducing any loss because of the switching the traffic source. The only difference between this one and the previous one is that the height of the peaks of the loss events are more irregular, because probably depends on what was the size of the couple of packets that you were sending at that point. That you will have more or less losses. And then in simple sharing codecs, you can see that there are constant losses. This is probably unusable. And I would like to insist, we want to show this, share with you, even if it's a work in progress. We want to share it because that was the first results we obtained with this new traffic source, this new model. There's work to do there, and we are convinced that, again, it's not a flaw in the algorithm, it's more something that we miss in the implementation, in the NS3 implementation, especially in NS2. As a summary, so we saw that what we did in NS2 and NS3, even if they are not exactly the same, the results we get are consistent, so this kind of validates each other. The results for the statistical codec, I didn't mention it at all, is because those results are very close to the ones with the perfect codec, so there were no news there, so nothing, I didn't want to take extra time here to present it. It seems like the ANADA is able to adapt very easily to this kind of noise in this, when it's modeled by the distribution mandated by the statistical codec, which is uniform. So we didn't show them here. And then we have seen that the performance degrades when you get to more involved traffic sources. For the trace base, you see a lot of noise. You could see a lot of noise but it could still, there were still few losses. And then for the content sharing codec, you have significant packet losses, and when the transient frames, like the transition frames, are sent by the traffic source. But I insist that we believe it's due to the absence of freight sharing. So we will, as soon as we get the rate-shaping buffer implemented, we will share with you the updated results for the traffic content sharing codec. So next steps, the first one, I'll start by the second half because this is what I've been saying all the time. So we have to implement the rate-shaping buffer in S3. We have to, otherwise we don't really see what's going on here. We didn't do it in the past because with the test that we were doing, we see that was not that necessary. But now we realize that it's really crucial to have it for this kind of behavior, of the traffic source. And we didn't present it today, but we are ongoing with the Wi-Fi test cases, and hopefully we will be able to present some material results shortly. And then on the first half, so updates to the draft, we would like to, this is important, align the terminology to the draft that Zahid presented. I guess the authors of the 3 candidates are going to do it, so we're going to be doing our part. And there is also extra text requested by the chairs to summarize, well, basically what we have presented here. So what is the status of implementation, what we have tried, what we haven't. And that is it.
Okay, thank you, Sergio, for that very good overview. And we are expecting the NADA draft to go to working group last call after that update.
Exactly. Yeah.
And unfortunately, we're very late in the agenda, so we're going to have to take questions and discussions offline in the break and on the mailing list.
I understand.
Okay, and Ingmar, you're up next.
Should we make it some 12 and a half minutes each, or I'll try to advance it through it in 10, 12 minutes.
If you can be a bit quick, that will be helpful, of course.
Yeah.
We have one more presentation.
Come.
We have one more after this. So
Okay.
very quick.
Okay, yeah. Yeah, and this is an update that is reasonably recent that's done, and what we have done is that we're going to merge it, sort of align the congestion control and rate control and the C++ implementation, so they are reflecting one another quite well, and have done some run through the large part of the test cases in the wireline test cases in the eval test. And what is actually asked for here is implementation experience, sort of implementing in browsers or in the clients and that stuff, and see how it actually works. And you have the C++ code, and it supports integration in clients. And what is needed is implementation RTPQ and RTCP. And for lack of better RTCP, you can use the RFC 3611 XR blocks, and that is explained in the draft. There is no ECN support yet in the C++ code, but it's trivial to add it, have it implemented in our system simulator already. And Rolf Globisch, who is with Fraunhofer in South Africa, has done some initial experiments on this and found some issues. And hopefully we have resolved some of these. They are related to how the bitrate is communicated to the video codec. Some mismatches there. And I would argue that this draft is ready for working group last call now. It has gone through some iterations on review also.
Jahed, I think the mismatch you're talking about is not about the algorithm, it's about the implementation part, right?
Yeah, it's how you implement and when you request a
This is a code implementation that has some issue, not the algorithm.
Yeah, because what Rolf has done is he was trying to satisfy some use cases. We're trying to run Scream over edge access, and you have really low bit rate there, and you need to account for the RTP header size more accurately than.
So just to comment on the draft status, so we would like to get something about the experiment section in there, and then we will take the draft to working group last call.
Okay, some suggested experiments or.
Yes, like we discussed, and we can discuss it further offline, what is required there, and maybe also want to update for terminology with the framework draft when you do it. But.
Yeah, great. And there is a lot of discussion around feedback intervals and per watt feedback. And here, Scream try to stress the algorithm and trying to find out in which region of the RTCP intervals does it work best. And in general, you need feedback every n received RTP packets, not the frames, RTP packets, and that keeps that clocking in a good mood. And I want to avoid that you have a per frame feedback, because you can drop one RTP packet in a frame and then you don't have any frame, and then you can stall that clocking unnecessarily. So it's better to have per n received RTP packet. And in order to constrain the RTCP overhead in the feedback, you should then transmit no more often than, say, 20 milliseconds. And to avoid deadlocking to low bit rates, especially if you try to run high bit rates, you should no more seldom than 200 milliseconds. And that is what it has been tried out, and then Scream works in a range of 20 kilobit per second up to some 10 megabit per second with those settings. And And then I would argue that the running Scream at the slow bit rate at 20 kilobits per second is not a really good choice, and it's better to use some more simple congestion control algorithm. But yeah, and a bit on the competing flows compensations, and there's been a lot of work trying to tweak that to work well. And the major problem with all these algorithms that there are also potential foot counts. In a sense, is that if you experience higher delay, then increase your tolerance to delay, and then you can easily cause self-inflicted congestion. And this algorithm tuning and this algorithm selection in Scream is based on sort of a compromise to avoid that you get self-inflicted congestion in LT test cases, and still manage these test cases for 5.6 and 5.7 fairly well. So it's a compromise, and still you have a risk of self-inflicted congestion. So if it's very unlikely that you have a competing TCP flows, then it's better to turn it off completely. So, and then I run test cases according to this eval test 03 draft, and it's actually based on my best current understanding, but some of these parts were a bit unclear to me, and I hope I got it right. And I tried a different few RTT means. I can't, but probably you need to read through the draft again and sort of point where I didn't really understand it.
So if you have some specific part, it would also be good to feed that back to the draft authors. Yeah, thanks.
And then after some email discussion, this test case 5.7, then I changed the rate distribution to a smaller interval, and just to get some results other than the zero screen bit rate. And 3 different RTT means and 2 different values of the network jitter. And also the other side, a maximum RTP-Q delay and some AQM specifics. And then I added also a slideshow example just to show why it works. So, and I won't bore you with all the graphs, and I'll go through can pinpoint the major findings. And if you run the test case 5.1, you see that larger round trip times generally give more delay spikes and jitter, and that is quite expected because it's Scream is sort of an algorithm that sort of tries to probe the bandwidth continuously, and then you naturally get more jitter and delay spikes. And in some cases, you can see that I can show an example where competing flows compensation in some causes of self-inflicted congestion, and you get increased delay, even though you don't have any competing TCP flows. Can go to the next slide here. And this, if you have 5 millisecond jitter, it looks reasonably good, and we can go through to the next. Here you look at the 200 millisecond round trip time and 30 millisecond jitter. You see that in the end of the graph, you see that the delay starts to increase. The lower, the right-hand side graph, and it's pointed out there. And that is an unwanted thing. But in some cases, in some generally in the more extreme cases, there are large round trip times, and you can get these problems. And they may not need to be there all the time, but they can sort of resolve themselves. So you don't get a delay. Generally, doesn't explode, but you can temporarily get higher delays unnecessarily. Okay, and then you have the case 5.2. Then the rate allocation is reasonably fair, and what can be pointed out here that the Scream has its own way of doing sending multiple streams. And that is a better choice if you have the same sending and receive endpoints. So it's better to send and use the same congestion control for both streams. So that's a better alternative one. And now we can scroll through this. And here, same high jitter and high RTT, you get some self-inflicted congestion as well. Okay. And congested feedback with bidirectional media flows. And one potential problem with Scream is that if you have reverse path congestion, then it should be more sensitive to that one, because that clocking will sort of halt because of that. And if you don't have any AQM, then you, in some cases you see the problems with that. We can scroll to the next page, and you see that that pointed out with the arrows or something like that. You see that the rate is temporarily reduced in the forward path if the backward path is congested. It doesn't blow up. It doesn't spoil the whole thing, but you can get some rate reduction just because of feedback path congestion. But if you run with Codel, next slide. Yeah, next slide here. Then you have less of these issues with reverse path congestion, because you don't. Reverse path congestion problems occur mainly because that the feedback is delayed, not that it's dropped. You can lose a couple of RTCP feedback packets without hurting the clocking that much, because you sort of always report accumulated received packets. So one lost feedback, it doesn't hurt that much. And yeah, can take next one. And then we come to this same congestion. You have a quite slow flow rate convergence. It takes a while for the flows to converge, as you can see in the next slide. It takes a while for the flows to converge. And oddly enough, if you have a more messy video codec, then convergence is actually faster. Because it's like you have a monkey in the cage that's sort of rattling the bars, and then you sort of converge more quickly. Get more noise in the system, and that helps convergence a bit. And if you want to avoid having this kind of slow convergence, and you know that you have the same sending and receiving endpoint, then it's better to set up 3 different streams and use the same congestion control and stream. And then you solve that very easily. Then you have sort of almost immediate convergence between the flow rates. Next one. And the test case 5.5, so it converges reasonably well, and you sort of managed to use the full bottleneck speed. And here we come to the sort of media, the hard part, actually, with the whole design exercise with Scream and possibly with other algorithms as well. And you have you don't get the optimal performance, and it is possible to improve the media bit rate, but then you increase the risk of causing self-inflicted congestion for other test cases, and if you try to run it on LTE or Wi-Fi or whatever. And so it's a compromise. And yeah, but can, if you use more proper AQMs, then you have less problems with the competing TCP flows. The main problem is if you have tail drop queues that are sort of reasonably large. I didn't even dare to try with a 1000 millisecond tail drop queue, because that I can almost assure you that it will fail. So the bad news. Yeah, and okay, we can scroll forward and look at the code results maybe. Here you have at least when you run with the Codel in AQMs and more sort of more shallow AQMs, then you get manage to get some throughput for the media, and which is shown here, and even with the reasonably high jitter in the network. And then we have sort of media flow competing with short TCP flows, and this is, I believe I will skip that for now. Okay. Because depending on how you configure it, you get reasonably good results or nothing at all. So it's completely unclear. I've tried 2 different, more relaxed sort of, or less intensive. Media pause resume is not that exciting anyway, so acceptable performance, and we can take this next here. Let's skip that one. It's at a slideshow example, and to get it working with slideshows, there are some tweaks that you need to configure this maximum RTPQ delay to very high values, because you don't want to drop packets, because this media slideshow frames, they can be really large. And then if you have a low throughput, they can be queued up quite long on this in the sender buffer. And you don't want them RTP packets to be dropped just because of that. And also the congestion window validation is preferably turned off. And that is also configurable in the C++ code. And also no rate control, because they don't. I don't see how you rate control the slideshow. Maybe you can do it and do some quality tuning and something. It's not like a video codec anymore. And we can look at the next slide. And here is the example. If you have a congestion window validation turned on, and then you you don't manage to use the bottleneck link fully, because the congestion window validation hits and reduces the congestion window. And a bit gory, for instance, now with this stuff quite a lot. And here it's better to turn off the congestion window validation for this case. You run some risk that the congestion window will grow uncontrollable, but there are other mechanisms to keep it limited by the number of bytes in flight. So that's wonder if there was any more. No, I believe we skip the question, comment, and leave to.
Okay, thank you, Ingmar. So we'll take the discussion and comments offline and in the mailing list. So, but I urge you to look at this, all of these presentations, as we have a lot of details that we were not able to cover.
So this is using FEC for congestion control. This work's done with Balazs Preet, who's not a co-author, but has been actually running all the tests for us as a grad student. Next slide. So quickly, the concept basically means instead of increasing the media bit rate, you send out a flurry of FEC packets based on the congestion control. What it believes is the amount of upspeeding it wants to do. So it can probe speculatively with more FEC or small amount of FEC, depending on what it believes the congestion control to do next. Once the FEC is added, it looks at the feedback, and if the feedback says, yeah, nothing got lost or some of it got lost, but we were able to recover, then makes another speculative increase in the media bit rate, and then maybe does some probing. So I'll skip through these two slides. It basically says that in a generic situation, you have this framework, and the next slide, we add an FEC module with an FEC code. The congestion control does not actually say which code you want to use, so it's free. It's up to the implementer to choose which one. So if you want to use XOR or something else, we insert the FEC module in between the RTP sender and the rate controller so that it can get all the feedback that's been received and make rate control decisions. Next slide. That's the state machine. There's a steady state where it does not do anything, the bitrate stays the same. In the probe state, it adds FEC. In the up or in the up state, it basically swaps out the FEC or reduces the amount of FEC and increases the media bitrate. Next slide. The feedbacks that we use is complementary. We need the lost packet information. We need the RLE of discarded packets, which is discarded by the jitter buffer, de-jitter buffer at the receiver, and packet counter loss and repaired packets to see if the FEC indeed worked correctly or not. Next slide. So this has been implemented over delay-based congestion control, which we're not, the results are based on that. There's a new paper coming out. Most of this is now implemented on OpenWebRTC and is working there. And we hope to compare this with Scream, for example, or some other mechanisms that are already in the OpenWebRTC suite. Next slide. So quickly, because I don't have much time, the test cases. This is using 4-man video sequence with the default VP8 encoder that's in OpenWebRTC. And here we see that kind of, the dark blue at the bottom is the amount of FEC that's added. You can see that when it goes down, the FEC is kind of removed. And whenever it's probing, you can see the increase in FEC. And the variation is not much. And what we've noticed is that the when we try to go down, sometimes the codec does not respond very quickly. So we probably need to like reach out to the team at OpenWebRTC and see if they've tweaked any of the numbers there because I saw a sharper decrease in the previous example slide set. So we probably need to see if this is something that we misconfigured or it's just an artifact of the congestion controller. Another thing to note is that we've been using very high RDCP reporting intervals, like 500 milliseconds, just to make sure that it kind of works when you have high delay scenarios. We could optimize it, and depending on the feedback that we've seen today, people are expecting to send feedback reports almost every frame or like 100 milliseconds. So we probably will tune this to see if the performance changes with the amount of RDCP feedback.
Mikul, very quick, I probably missed that. Which congestion control are you using right now?
That's our own.
Okay.
It's a delay-based congestion control. And test case 2, this is two flows competing with each other. And here you can see that the combined actually works very well. And the performance is quite comparable to the other other congestion controls that we've seen proposed in the group. Next slide, which is test case 4. Here again, we see convergence quickly. So nothing to worry about in the sense that there is a good ramp up. And when the other congestion controls appear, we start to see the convergence of the congestion control. And in this case, we also see that the FEC performs pretty well in providing tolerance. There are more details that are going to come out in an ArcSep paper, hopefully by the end of this month or early next month. So again, as the RTT increases, we see better performance as the FEC starts to play a more important role. So the next slide, again, you'll see the convergence is far more quicker than in the previous case where the 50 millisecond scenario. There's a lot being said about the TCP. So we ran some test cases on the TCP. So this is the long TCP. This is 50 milliseconds. The next slide, 150 milliseconds. The next slide. So we see that we are at least able to maybe not compete. We're not totally aggressively pull down to like the basic media bit rate. We do achieve 100 kilobits per second, 1000 kilobits per second at some intervals of time. Next slide, which is about the 50 millisecond RTT and short TCP. Here we see the performance drops to like 500 kilobits per second. I wonder, I've seen different results, and I think this seems to be doing a slightly better than the other ones. If you go down, actually, as the RTT increases, the performance becomes slower. So here you can see actually towards the end, you even see a white area where the TCPs actually stop for a brief moment of time, and the RTP is able to ramp up. But if you go to the next slide, you'll see that again the RTP in this case again goes up when the TCP stop, so it's responsive. But as the RTT increases, it drives the congestion control in this case to a lower operating point. And in this case, we would see that with 300 milliseconds delay, we're actually hitting the lower bound of the video bit rate, which is what some of the others also showed. So I think this is the end of my slide, which is, I think the next slide is, so we've shown some results. If you've shown the last time we showed results were, I think early last year. We took a break from showing any results to let the rest of the group actually do the congestion control work. We're still looking at the fact that we have a mechanism that the FEC works with. If there's not enough energy in the room to like use FEC as part of their mechanism, then we would propose our congestion control, which makes use of the FEC. And we're working on extending it to multipath, so maybe we just do it and see what the group thinks. So there would be a fourth one. So there are two ways of doing it. Either we bring two documents, one which is the generic FEC, and then the congestion control that uses FEC, and that way there would be two documents here, and we can see which one or both may move forward.
Mozanetti, it seems like an interesting and useful approach. One thing though is that this should have a note well on it because there's 2 IPR declarations against it.
Yep.
And neither one of them have any licensing terms. So it'd be good if you can force people to get some clarity about what the licensing
We
terms are gonna
discussed
be.
I think the IPR came like very early on, like almost 2.5 years ago. We did bring it up to the group, and the group did not seem to.
Well, my concern is there's no licensing terms given on the IPR. So if we could force Polycom and Nokia to give some sort of guidance about what the terms would be, then it
I think if the people are in the room, they probably would be able to say more. But as an individual which doesn't work for either of the 2 companies, I'm probably not going to say anything about it.
Okay. So my question was like, well, did you see any difference because you said like FEC could be as a like generic mechanism for all the algorithms. Do you feel like if the algorithm, the performance of this FEC based probing will differ between the different algorithms? Or is there any? I mean, I'm trying to get like if it is because I would like to see this is more a generic mechanism, but I couldn't like. What is the need for tying it to the condition control? I mean,
so one of the things that I noticed early on when we did the study, like way back in 2012, and we kind of looked at Chrome's code and implemented this in NS2 with Chrome's GCC. We did see that it does improve performance. It gets better stability, especially with the video. We can play back the video, right? So we see a better performance in terms of like how the video plays back at both ends. In terms of with FEC. So I think that it's and that's one reason why we've not proposed it as an alternative congestion control, and we've kind of waited for the community to catch up. But I think in some sense my patience is at ends. We would like to either see this move forward, or actually have stepped back for the last 18 months to let the group do what it wanted to do. What I'm seeking now is to see if there is energy to move this as an independent method, or because we have all the results, we have a congestion control, we can which uses it, we can easily document it. We've been running it for the last 6-7 years, and we have phenomenal experience in implementing it in 3-4 code bases. So we could just bring that.
Yeah, I mean, I still missing this. I mean, what exactly? The proponents, the 3 proponents we have, what exactly we need to do? I mean, to show you results with probing, because
I think it's an exercise in for each of those congestion controls to actually look at it and say if they want to use it. If there's no incentive for you guys to implement it, then perhaps we will bring our own congestion control, which uses the FEC.
But I still don't get why you would like to bring your own congestion control.
Because, well, I think it's useful. And the other thing is that we've given ample amount of time for other people to pick it up.
But
and
I agree with that it's useful, but useful in a generic way. I mean,
I think so. But like, there are results which have been published a couple of years ago. We've initially, when everyone was presenting the results, we presented ours, and we've shown that there's compelling evidence to use it. The feedback that we got initially was that it was a generic mechanism that people wanted to use. So, and that's why we did not pursue our own mechanism, just to allow the community to use it. But having waited a certain amount of time and not seen any like uptake on it, I have a feeling that we probably need to move forward with our own mechanism using this, while keeping the other document. I think we'll probably keep the generic document and add
Right, but it would be at the end of the day up to the respective algorithm to decide and to define at which point, which state transitions you do, how many packets you're going to send for the next time unit as FAC packet and as other, and which FAC algorithms to use and so forth. But that's nothing that this algorithm can do for any of the other drafts, right?
So we're running out of time, so we're cutting the line after the 2 of you. So short comment.
Michael Romalo again. I've got no problem with this document being an individual document. I think Mo's voiced a concern that we need some specificity on the IPR declarations that have been filed against it. I would recommend that that occur before any kind of formal adoption. But lastly, the exact manner in which you put FEC is kind of underspecified. It actually leaves a little bit more room for other people to do other innovations with respect to small tweaks on what FEC they may want to put in. And I have a feeling that some of the participants in the room probably experimenting are along those lines and probably don't feel a need for any of those detailed, perhaps even competitive, differentiations to be aired out in such a group. So I don't know what to go beyond this, other than I have got no objection to this remaining an individual document. Thank you.
I think individual documents, like no one can stop them from coming. So I think I think that's not really a valid point. The fact is that the code block is something that you can use yourself. So we don't say if it has to be XOR or Reed Solomon or Raptor or anything else. So it's up to the individual companies or proponents to use whichever mechanism they've already licensed from someone or have developed themselves. What we do show is that irrespective of what mechanism you use, even with a simple XOR mechanism, you're able to go very far with it. So, and get better performance. So I believe that there is a need for it.
Okay, so we are really running out of time, so we have to continue this discussion on the list and on the side. So thank you all for coming. And we've had a lot of discussion here and also a lot of results that we had time to look at in detail. So please keep that energy and the discussion on the list and in the hallways. Thank you.
Good job.
What were you saying?
Just say the outcome again in the mic so remote people know what the numbers, because they can't hear anybody. Yeah.
It's kind of annoying that you can manage the slides for people.
Yeah.
Or it's just a bit.
Yeah, that's why you need, I think, two people, so you have actually another editor or something. Yeah.
Candidates are asking to present